In the previous lesson, we looked at singleton objects, and we also looked at the notion of companions, where we say class recipe and object recipe. Since those both have the same name and they're defined within the same compilation unit, in other words, the same file, we call them companions. Now, we saw a very common use case for companion objects, which is a place to provide factory methods like make here. It turns out this is such a common pattern that Scala provides a little bit of syntactic sugar to help us out. So let's take a look at this. In the interpreter, we can say something like val list is equal to list 1, 2, 3. We've seen this sort of thing many times already in previous lessons, and when you saw this before, you might have wondered, well, how does this work? Normally when we instantiate objects, we have to use the new keyword. So what's special about lists? In fact, even if we wanted to, we couldn't say new list 1, 2, 3, because list is abstract. Well, it turns out that there's a companion object to the list class, and the companion object isn't abstract. It's something we can use directly. It has a method defined on it called apply. The apply method returns some sort of concrete default implementation of list, the details of which are hidden from us. So list.apply 1, 2, 3. So when we say list of 1, 2, 3 like this, it's literally just syntactic sugar, just shorthand for list.apply 1, 2, 3 like this. So the apply method is really just a normal method that Scala happens to give a little bit of special significance to. In order to use this, all that we have to do for our factory method is to just name it apply. So now, instead of calling recipe.make, we can just say recipe. This is a very, very standard pattern. So let's clean our code up just a little bit. Let's make the constructor public again, just because private constructors aren't super common. And let's also take out the defaults, because that's not that common either for constructor parameters. It's much more common to supply them in the apply method instead. There we go. I'm also going to take out the print lines, just because we've already demonstrated our point with those. And now this is starting to look much like more sort of standard idiomatic style Scala code. So if you had previously been wondering about why we didn't have to say new with lists and maps and so forth, well, now we know our answer. It's just the apply method on the companion object. There's also one more thing that you might have been wondering about, something that possibly seemed magical before, which is how does pattern matching work? Right? We could say something like list match case list of A, B, and C. And what that is doing is essentially sort of the opposite of a factory, or the opposite of a constructor. It's taking an existing list and decomposing it using this list pattern into its constituent parts, these elements A, B, and C. In general, we call this an extractor pattern because we're extracting the properties of an object. Well, if the idiomatic way of building objects, composing them from their constituent parts, is using a method called apply, then you might guess that the idiomatic way in Scala of decomposing an object, extracting its parts, should be a method called unapply. To explain a little bit about the mechanics of how unapply works, we need to see a couple things first. The first thing we need to see is something called tuples. So a tuple is simply a way of taking a few values and grouping them together to make a single value out of them. So let's make a tuple out of the number 1, the string hello, and let's say the list 1, 2, 3. All right. So we have a tuple. The tuple has 3 elements, and the first element is an int, second element is a string, and the third element is a list of ints. To make this a little bit more explicit, this is actually also a syntactic sugar for saying tuple 3 of 1, hello, and list. Tuple 3 is the name of a class that's built into the standard library. The standard library contains tuple classes of all different sizes. You might ask, why do we have different classes for each different sized tuple? And the answer is because we have to keep track of the heterogeneous types inside of them. Right? With a list, well, a list can be of any size. right? A list of 0 elements is the same type as a list of 10 elements or a list of 100 elements, because the elements are all of the same type. We can just say list of int. But with a tuple, since the elements are of different types potentially, like we have here, int, string, and list of int, we have to be very specific when we're keeping track of those types. We're keeping track either of 3 different types, or 4 different types, or 5 different types, and so forth. At any rate, this is pretty transparent to us. When we construct a tuple, all that we need to do is just group values together. The other thing that I want to demonstrate before we get back to unapply is option. Now, we've seen option once before in the context of exception handling. We said that option is a way of representing the possibility of failure in a computation. So a quick example of a kind of computation that could fail would be dividing two numbers, right? Because division by 0 isn't allowed. Let's define a method, safe divide. It'll just take 2 ints, so let's call this one x, and call this one y. And instead of producing an int, it'll produce an option of int. And this represents the possibility of failure. So the way that we would implement safe divide is if y is equal to 0, then we'll produce none. That's our failure case. And in our success case, we'll produce sum of x divided by y. So I can say safe divide. Let's say we want to divide 4 by 2, so that should be okay. But if we want to divide 4 by 0, that's not okay, of course. Well, so why were these two things important for unapply? Well, tuples are important because if we're trying to extract properties of an object, we need something to put those properties into in order to return them. So that'll be our tuple. And the reason why option is important for pattern matching is because pattern matching, as we know, patterns might not match. That's a kind of a failed computation. So our unapply method is going to end up returning an option of a tuple containing the properties that we've extracted from our object. So let's go ahead and implement this now that we've got these tools. We've got our apply method, and we're also going to implement unapply. Now unapply is going to take as input a recipe. This is what we're going to try to extract the properties of. And the return type, like we said, well, it's going to be an option of a tuple of the recipe's properties. So those properties are both of type list of string. So the way that we implement this becomes relatively straightforward. We need to construct a tuple of the recipe's ingredients and the recipe's directions, right? Those are our properties that we're extracting. And we need to wrap that tuple in an option. Now keep in mind, this is actually a very simple sort of unapply method. If we get a recipe in, we'll always succeed. So we can just say sum. So no need to worry about a successful case and a failing case here. We're just going to always match. So now that we've defined our unapply method that takes a recipe and extracts its fields into a tuple, we can now use the recipe companion object as an extractor. So let's see how that works. Let's use this to extract the fields of our peanut butter and jelly recipe. So we'll say cookbook.pbj match. And now since we've defined our unapply method, we can say case recipe ingredients and directions. Again, what is this doing under the covers? Well, it's calling recipe.unapply. And the thing that's a little bit unintuitive here is that it's not calling unapply with these as the arguments. It's calling unapply with this as the argument, right? This is an existing recipe object. That's the parameter to unapply. And then this is actually the return value from unapply. This is our tuple of ingredients and directions. So we can use these. Let's just print them out. And there we go. Now keep in mind also that we can nest patterns. These didn't have to be just variable binding patterns in here. These could have been patterns that match some aspect of the lists. So let's see an example of composing patterns. Let's define a method that will determine whether or not a recipe is simple. And the way that we'll determine that is just by saying, well, is there only one step in the directions? So let's say def is simple. It'll take a recipe, and let's say it'll produce a Boolean, just a yes or no. And the way that this will work is by matching on the recipe. So we'll say recipe match case recipe. Again, this is calling recipe.unapply using this recipe as the input. Now we don't care about the ingredients, so we'll ignore those. We'll just use the wildcard pattern. And we say we want to only match recipes whose directions have a single element. So we'll compose our recipe pattern with our list pattern. We'll say a list containing a single element. And a case anything else, well, that's not a simple recipe. Okay, so is simple cookbook.pbj true? And is simple cookbook.bacon pancakes? That's also simple as well, right? Because both of those recipes have only one step in their directions. So that's the basics. We've seen apply, and that's our factory, our way of creating objects, shorthand. And we've seen unapply. That's our extractor, our way of decomposing objects as a shorthand as well. But unapply is actually just a little bit more powerful than what I've shown you already, because we don't have to use unapply in this sort of cookie-cutter pattern. We don't have to just use it to extract fields of an object, but we can also use it to match whatever properties we want. Let's say we want to define a pattern that matches even numbers only. And if it matches the even number, it'll extract the value of that number divided by 2. The way that we can do that in Scala, again, is using an object. We'll call it object even. And we'll define a method unapply. Well, what we took as input to the recipe objects unapply was an instance of the recipe class. In this case, we're not going to have a constraint like that. We don't have an even class or something like that. We're just going to take an int. And in fact, in general, unapply can take anything that you want it to. So let's say that our unapply will take some number as an integer, and it'll produce an option of int as a result. So the way that we'll implement this is if the number is divisible by 2, if n mod 2 equals 0, then we'll return sum of n divided by 2. Else, what do we return? None. Okay. So we can call even.unapply by hand, right? Unapply of 4, that should be sum of 2, and unapply of 3, that should be none. But because we've followed this unapply convention, we can use it in a pattern. So I can say for match case even, and what are we extracting? Well, we're extracting the value of half of 4. So let's say half, and we'll just return that. Okay. If we try to say 3 match, then what do we think is going to happen here? Well, this pattern won't match. 3 isn't even. It's going to return none, like we saw. So therefore, the case falls through. And when you reach the bottom of a pattern match expression without any cases matching, well, the pattern match expression fails. We get a match error. Now, this is bad style, of course. You don't want the possibility of match errors in your code. You want your patterns to be exhaustive. In other words, you want them to cover all possible cases. So, in our case here, we'd probably want, just like we had an even pattern, we'd probably also want something like an odd pattern to cover the other case. So unapply is very powerful. It's generally used the way that we've used it here in recipe, right? Recipe's apply method takes ingredients and directions and produces a recipe, while unapply takes a recipe and produces a tuple of ingredients and directions. They're very simple, and that's sort of the standard pattern. But what we've seen is that you can use pattern matching to extract really anything that you can dream of. We're going to use that later in our calculator.